There is a smudge of light in the night sky that has haunted human imagination for longer than we have had words to describe it. You can see it with your naked eye on any clear, moonless night. It sits in the constellation Andromeda, barely visible, hovering at the edge of perception. Not a star, not a planet, just a soft, pale blur against the dark. Ancient astronomers noticed it. Medieval scholars catalogued it. For centuries, nobody knew what it was. A cloud of gas, perhaps? A distant nebula within our own stellar neighborhood. Then, in the 1920s, an astronomer named Edwin Hubble trained a powerful telescope on that faint smudge and measured something that changed everything. It was not a nebula. It was not part of our galaxy. It was an entirely separate galaxy. A vast, spinning collection of approximately 1 trillion stars, sitting 2.537 million light-years away from Earth. 2.5 million light-years. The light reaching your eyes when you look at Andromeda tonight left that galaxy before our species existed, before Homo sapiens walked the Earth, before we made tools or fire or language. That light has been crossing the void of space for longer than humanity has been human. Tonight, we are going to ask a single extraordinary question. What would it actually take to go there? Not in theory, not as a vague aspiration, but in real, precise, physical, human terms. What would it take to build a ship, recruit a crew, and attempt the crossing of 2.537 million light-years of empty space to reach another galaxy? The answer is one of the most fascinating, most terrifying, and most humbling things science has ever produced. Settle in. Let your body grow still. And let's begin. The distance that changes everything. Before we talk about ships, or engines, or crews, we need to truly understand what 2.537 million light-years means. Not as a number. Numbers at this scale are easy to say and impossible to feel. We need to understand it the way you understand something that matters, in your bones, in the part of your mind that processes reality rather than abstraction. A light-year is the distance light travels in 1 year. Light moves at approximately 186,000 miles per second. In a single second, it crosses the distance from New York to Los Angeles more than 60 times. In 8 minutes, it crosses the entire distance from the Sun to the Earth. In just over a second, it travels from the Earth to the Moon. Now, multiply that by 2.537 million. That is the distance to Andromeda. When that light, now entering your eyes, left the Andromeda galaxy, the world looked nothing like it does today. The Sahara was green. The Mediterranean coastline was shaped differently. Ice sheets covered large portions of the northern hemisphere. And our ancestors, our actual biological ancestors, the creatures from which we are directly descended, were small, upright primates with simple stone tools and no concept of fire. Homo sapiens as a species did not yet exist. The light you see when you look at Andromeda is older than our species by a significant margin. this is not a poetic metaphor. It is a measurable, verified physical fact, and it matters enormously for what follows, because any journey to Andromeda is not simply a journey across space. It is, in the most literal possible sense, a journey across time. Now let us talk about speed. Specifically, let us talk about what it means to travel fast enough to cross this distance. Our fastest spacecraft ever built is the Parker Solar Probe. At its maximum velocity, achieved when it swings around in close proximity to the Sun, it reaches approximately 430,000 miles per hour. This is genuinely extraordinary by any human standard. At this speed, you could circle the entire Earth in roughly 3.5 minutes. You could cross the Atlantic Ocean in under a minute. You would travel from one coast of the United States to the other in about 20 seconds. But let us do the mathematics for Andromeda. 2.5 million light-years is approximately 14.9 quintillion miles. That is a 14 followed by 18 zeros. At 430,000 miles per hour, the Parker Solar Probe would take approximately 3.9 billion years to reach Andromeda. For context, the Earth itself is only 4.54 billion years old. If you had launched a spacecraft moving at this speed at the moment our planet first formed from the collapsing cloud of gas and dust, it would be arriving at Andromeda sometime around now, just as you are lying here listening to this. During that journey, every ocean on Earth would have formed. Every continent would have drifted to its current position. Every species that ever existed on this planet, every trilobite, every fern, every dinosaur, every mammal would have evolved, flourished, and vanished. The entire evolutionary history of life on Earth, from its simplest chemical beginnings to the creature listening to these words, would have played out as background noise to that journey. Obviously, that is not a viable travel plan. So we push harder. We imagine engines that do not yet exist, propulsion systems that push physics toward its outer edges. What if we could travel at 1% of the speed of light? That is 1.86 million miles per hour. Roughly 4 times faster than the Parker Solar Probe at its peak. At this speed, relativistic effects begin to appear, though they remain minor. The trip to Andromeda would take approximately 253.7 million years. Still completely impossible. What about 10% of light speed? This would require propulsion technology far beyond anything we currently possess. Perhaps nuclear pulse propulsion, in which a spacecraft rides repeated nuclear detonations, like a surfer riding waves, or a Bussard ramjet, a theoretical engine that scoops hydrogen from the interstellar medium and feeds it continuously into a fusion drive. At 10% of light speed, the journey to Andromeda takes about 25.4 million years. Better, still hopeless. 50% of light speed? The journey takes roughly 5.1 million years. At 90%, about 2.8 million years. At 99%, approximately 2.6 million years. Notice something strange happening in these numbers. As we approach the speed of light, the journey time drops, but it does not drop nearly as dramatically as the speed increase would suggest. Going from 10% to 90% of light speed, a 9-fold increase in velocity, only reduces the travel time from 25 million years to 2.8 million years. The universe's architecture seems almost deliberately designed to keep Andromeda out of reach. And then something remarkable happens. At very close to the speed of light, say 99.999%, something called time dilation enters the picture. And time dilation changes everything. Time dilation and the horror of relativistic travel. Time dilation is one of those concepts that sounds like science fiction, but is in fact one of the most precisely confirmed predictions in all of physics. It has been measured with atomic clocks on airplanes. It is built into the calculations that make GPS satellites work accurately. It is not speculation, it is reality. Here is what it means. According to Einstein's theory of special relativity, time does not pass at the same rate for all observers. The faster you move relative to someone else, the more slowly time passes for you as observed from their frame of reference. This effect is negligible at ordinary speeds. The difference between a person on a fast train and a person standing still is measured in fractions of a fraction of a nanosecond over a lifetime. But as you approach the speed of light, the effect becomes extreme. At 99% of light speed, time for a moving traveler passes at roughly 1/7 the rate it passes for a stationary observer. At 99.9%, the ratio is about 1 to 22. At 99.99%, roughly 1 to 70. At 99.9999% of light speed, the numbers become extraordinary. The traveler experiences time passing at roughly 1/10,000th the rate of the universe around them. What does this mean for our journey to Andromeda? At 99.999% of the speed of light, a speed we have absolutely no idea how to achieve, but which physics does not forbid, the subjective experience of the journey for the crew aboard the ship could be compressed to as little as a few decades. The crew ages normally. They eat breakfast, sleep, work, argue, make discoveries, feel tired, feel rested. 20 years pass for them, maybe 30, maybe 40, depending on the precise velocity. But outside the ship, the universe ages at its normal rate, and the universe, during those subjective decades, advances by approximately 2.5 million years. Let that settle in for a moment. You board a ship. You say goodbye to your family, your friends, your home. You spend 30 years in the ship, subjectively, from your own experience. You arrive at Andromeda, and from Earth's perspective, 2.5 million years have passed. Everyone you have ever known is not just dead. Their descendants, thousands and thousands of generations of descendants, have lived and died. The languages they spoke do not exist. The countries they lived in do not exist. The cities, the technologies, the art, the music, the entire cultural fabric of the civilization they inhabited, gone. Replaced repeatedly over geological timescales by things you cannot imagine. The Earth you left no longer exists in any meaningful sense. It may still orbit the Sun. The Sun itself will still be shining. It has another 5 billion years before it begins to die. But the Earth that was your home, the civilization that was your context, the species that was your kin, all of it has been transformed beyond recognition or erased entirely. Your departure was not just a journey. It was a one-way door out of your own time. This is what physicists sometimes call the twin paradox, extended to its most extreme possible conclusion. If one twin boards a relativistic spacecraft and the other stays on Earth, the traveling twin returns younger. The faster the travel, the more pronounced the effect. At near light speed, the difference is not years, but millions of years. The traveling twin steps off the ship into a world that has aged millions of years, while they have aged decades. There is no way to cheat this. Time dilation is not a trick. It is not an error in the calculation. It is the actual physical behavior of time in a universe governed by the laws of relativity. The universe ages, while you do not. You can compress your own experience of the journey, but you cannot compress the universe. And this creates a particular kind of horror that is different from every other challenge of this mission. Most risks you can prepare for. Radiation, you can add shielding. Mechanical failure, you can build redundancy. Isolation, you can select psychologically resilient crew members and design the ship carefully. But the passage of time outside your ship, you cannot prepare for that, because there is nothing to prepare for. It simply happens. The universe moves on without you. And when you arrive, there is no going back. Not because the journey in the other direction is physically impossible, but because the Earth and civilization you knew have been gone for 2.5 million years. You are separated from home not by distance, but by time. And time, unlike space, only moves in one direction. This is why the journey to Andromeda is unlike any other journey humanity could attempt. It is not just an adventure. It is an exit. A permanent, irreversible departure from the era in which you were born, the people who made you who you are, and the world that gave your life its meaning. Every member of a crew that attempted this mission would know this before they left. The question of whether anyone could genuinely absorb that knowledge, not just intellectually, but emotionally, in the deep and personal way that makes decisions real, is one of the most profound psychological questions the mission would raise. We will return to that question, but first we need to understand how such a ship would actually work. The engineering of the impossible. Propulsion. Let us now descend from the philosophical into the brutally practical. You want to build a spacecraft capable of reaching 99.999% of the speed of light. What does that actually require? The answer begins with energy, specifically with an almost incomprehensible quantity of energy. In classical mechanics, the kinetic energy of a moving object is 1/2 times its mass times its velocity squared. Simple enough. But this formula breaks down at relativistic speeds, because as an object approaches the speed of light, its effective mass, from the perspective of an outside observer, increases The faster it goes, the more energy is required to push it faster still. And as velocity approaches light speed, the energy required approaches infinity. This is not a solvable engineering problem. It is a fundamental property of space-time. Nothing with mass can reach the speed of light, not because our engines are not powerful enough yet, but because the universe does not permit it. But we can get very close. To accelerate a spacecraft with a mass of 10,000 metric tons, roughly the mass of a large naval vessel, to 99% of the speed of light, requires approximately the total energy output of our Sun over several full days. To reach 99.999% requires more still. We are talking about quantities of energy that dwarf the entire output of human civilization since the Industrial Revolution, condensed into the propulsion system of a single ship. Where does this energy come from? Chemical rockets, the technology that carried humans to the moon, are completely out of the question. The best chemical rocket engines achieve exhaust velocities of roughly 4.5 kilometers per second. The speed of light is approximately 300,000 kilometers per second. The gap between these numbers is not an engineering challenge. It is a category difference. Chemical rockets, no matter how numerous or how efficiently staged, cannot approach the velocities required. Nuclear fission offers improvement. The energy density of nuclear fuel is millions of times greater than chemical propellants. Some concepts from the 1970s, like Project Orion, proposed spacecraft powered by repeated nuclear detonations, a ship riding its own controlled nuclear explosions, each blast pushing the vessel forward on a massive shock-absorbing plate. At its most ambitious, Orion concepts could theoretically reach a few % of light speed. Not enough for Andromeda on any human timescale, but a dramatic improvement over chemical propulsion. Nuclear fusion is more promising still. The fusion of hydrogen isotopes releases energy at an efficiency roughly 4 times greater than fission, and with significantly less radioactive waste. If we can build a working fusion drive, and despite 60 years of effort, we still cannot sustain a net positive fusion reaction, it could theoretically push a spacecraft to perhaps 10% of light speed. Still not enough. The most theoretically efficient propulsion mechanism possible is the photon rocket. This is a drive that converts mass directly into photons, particles of light, and ejects them from the rear of the spacecraft. Since photons move at exactly the speed of light, this is the maximum possible exhaust velocity. It is also, theoretically, 100% efficient in terms of converting mass to momentum. Nothing can be more efficient than this within known physics. But even a photon rocket faces the brutal mathematics of the rocket equation. As the desired final velocity increases, the initial fuel mass required grows exponentially. For relativistic speeds, the required fuel-to-payload ratio becomes staggering. You need enormously more fuel than ship. The ship carrying the fuel to carry the ship to carry the crew becomes a recursive nightmare of escalating mass. This is why many theorists have turned to external propulsion. A laser sail works by directing an intense beam of laser light at a large, highly reflective sail attached to the spacecraft. light carries momentum. When it strikes and reflects from a surface, it imparts a tiny push. A large enough sail, illuminated by a powerful enough laser, can be accelerated to a significant fraction of light speed without carrying any fuel at all. The laser stays at home. The energy source stays in the solar system. The spacecraft is just a sail and a payload, accelerated by a beam from far behind. This elegantly sidesteps the rocket equation. Since you are not carrying your fuel, the mass ratio problem largely disappears. The Breakthrough Starshot Initiative has seriously proposed exactly this kind of system for sending tiny probes to Alpha Centauri at roughly 20% of light speed. The physics works in principle, but the challenges for a crewed mission to Andromeda are severe. A sail capable of carrying a large crewed spacecraft would need to be vast, potentially hundreds of miles across, while being almost vanishingly thin and light. Any imperfection in the material, any tear, any contamination would compromise its function. The laser array required to push it would need to be the most powerful device humanity has ever constructed, powered by an energy source capable of sustaining its output for years. And then there is the problem that no one has a good solution to. A laser sail accelerates you beautifully, but it cannot slow you down. The laser is behind you, not in front of you. As you gain speed and cross the vast distances between here and Andromeda, you leave the laser far behind. When you want to decelerate, there is nothing pushing against your forward motion. You are moving at 99.999% of light speed toward a galaxy. Without deceleration, you will simply pass through it and continue into the intergalactic void on the other side, having crossed 2.5 million light-years, only to miss your destination entirely. So you must solve deceleration. And deceleration is, in many ways, even harder than acceleration. One option: carry your deceleration fuel with you from the start. This reintroduces the rocket equation and all its exponential unpleasantness. The fuel required to decelerate a large ship from near light speed is approximately equal to the fuel required to accelerate it, which means you effectively need to double your fuel load, which then requires more fuel to carry that fuel, which requires more fuel still. Another option: deploy a magnetic sail as you approach Andromeda. An enormous superconducting loop generates a powerful magnetic field. This field interacts with the ionized gas of the interstellar medium, the thin, sparse plasma that fills the space between stars. The charged particles in this medium push against the magnetic field, creating drag, slowing the ship. The interstellar medium is extraordinarily thin, perhaps a few atoms per cubic centimeter, so the deceleration is gentle, extremely gentle. Depending on the density of the medium you encounter, deceleration could take decades or centuries of ship time. Another option: antimatter annihilation. When antimatter meets normal matter, the two annihilate completely, converting their combined mass into pure energy with 100% efficiency. This is the most energy-dense fuel theoretically possible. A few kilograms of antimatter could release more energy than a conventional nuclear warhead. Used carefully in a directed drive, antimatter could provide efficient, powerful thrust for both acceleration and deceleration. The problem is production. Currently, the world's most advanced particle accelerators produce antimatter in quantities measured in billionths of a gram. Scaling to the kilograms or tons that an Andromeda ship would require is not a near-term engineering challenge. It is a civilization-scale undertaking, potentially requiring a factory powered by a significant fraction of the sun's energy output. And storing the antimatter once you have produced it requires perfect magnetic containment. Any contact with normal matter causes instant, total annihilation. A containment failure does not cause a fire. It causes an explosion that vaporizes the ship. We do not yet know how to solve propulsion for this mission. That is an honest statement. The physics does not forbid a solution, but the specific solution remains genuinely unknown. Radiation, dust, in the ship that must not fail. Suppose propulsion is solved. The ship exists. It is accelerating. Within some number of years of ship time, understanding that the universe outside is aging at a different rate, it reaches 99.999% of the speed of light and begins its long crossing. What does space look like at that speed? And what is space actually doing to the ship? The first thing to understand is that space is not empty. This is a common misconception. The vacuum of interstellar space does contain matter, extraordinarily thin and sparse by any earthly standard, but present. Between the stars of our galaxy, there is an average of perhaps 1 atom per cubic centimeter, mostly hydrogen. It is called the interstellar medium, and at ordinary speeds it is essentially harmless. At 99.999% of light speed, it is not harmless at all. When you are moving at near light velocity, every hydrogen atom you encounter is not sitting still relative to you. From your perspective, each one is approaching at 99.999% of light speed. The kinetic energy of a single hydrogen atom at these relative velocities is comparable to the energy of a high-energy particle in a physics laboratory accelerator. When this atom strikes the hull of your ship, it does not bounce gently. It creates a cascade of secondary radiation, a tiny but real particle physics event occurring millions of times per second across every square centimeter of your forward surface. The ship's forward hull becomes, effectively, a continuous particle collider. This is manageable with sufficient shielding, but the shielding must be substantial. Dense material, lead, polyethylene, water, or some future composite, positioned ahead of the crew compartment to absorb and scatter the incoming particles. The shield gradually erodes as atoms strike and chip away at it. The crew must monitor its thickness continuously and may need to deploy additional material as the journey progresses. But individual atoms are not the worst threat. Dust grains are. The interstellar medium contains not just individual atoms, but microscopic particles, grains of matter, sometimes as small as a bacterium, made of silicates, carbon compounds, ice, and metal. At normal velocities, these grains are trivially harmless. They have essentially no effect on anything they encounter. At 99.999% of light speed, a single dust grain with a mass of 1/1,000,000th of a gram carries kinetic energy equivalent to a substantial explosive device. If it strikes your hull, it does not scratch it. It punches through like a meteorite impact in miniature, vaporizing material on contact, sending shockwaves through whatever it hits. The solution is a sacrificial shield, positioned far ahead of the main ship, a large block of dense material designed to absorb these impacts, gradually wearing away throughout the journey. The shield protects the ship, but the shield itself is consumed. You need to carry enough shield mass to last the entire crossing, which is another mass penalty added to the already immense engineering challenge. Active shielding is another option. Powerful magnetic fields ahead of the ship could deflect incoming charged particles. Lasers could vaporize dust grains before they reach the ship. Both approaches require continuous energy, gigawatts running for decades. Now consider what the journey looks like from the crew's perspective. At near light speed, the way the universe appears undergoes a dramatic transformation. This phenomenon is called relativistic aberration, and it is one of the stranger consequences of traveling at these velocities. As you accelerate toward light speed, the light reaching you from objects ahead gets compressed and blue shifted, pushed toward the blue and ultraviolet end of the spectrum, appearing brighter and more energetic. The light from objects behind you gets stretched and redshifted, fading toward infrared and eventually disappearing entirely. Stars that would normally be distributed across the entire sky appear to migrate toward the forward direction, compressed into a narrowing cone directly ahead of the ship. At 99.999% of light speed, essentially all the light reaching you appears to come from a single point directly ahead. The sky behind you is black. The sky to your sides is black. Everything is concentrated in a blazing disk straight in front of you. And this is not just starlight. The cosmic microwave background radiation, the afterglow of the Big Bang, normally a faint and uniform glow at a temperature of about 2.7 degrees above absolute zero, invisible to human eyes, becomes Doppler shifted. At near light speed, this background radiation is boosted into visible light and beyond, flooding the forward view with intense radiation that the crew must be shielded from. The universe at near light speed does not look like the universe in any astronomical photograph you have ever seen. It is alien, compressed, intense, and beautiful in a way that nothing biological was ever designed to witness. Navigation in this environment is genuinely challenging. You cannot simply look where you are going in any normal sense. The visual information available is distorted and compressed. Detection of hazards ahead, a rogue planet, a dense dust cloud, a region of unusually high interstellar density, must be done by instruments, not eyes, and done well in advance. At near light speed, course corrections are expensive. Changing direction requires firing thrusters to alter velocity. And at relativistic speeds, every change in velocity costs enormous energy. The turning radius of the ship is measured not in miles, but in light years. If you detect a hazard and need to avoid it, you must begin the maneuver years or decades before the encounter. Waiting until the hazard is visible in any practical sense means you have already hit it. This means the route to Andromeda must be mapped in exquisite detail before departure. Every known hazard catalogued, every course correction planned, decades in advance, and built into the mission profile. The margin for improvisation is essentially zero. The human animal in an inhuman environment. All of the engineering challenges we have discussed so far are, in principle, solvable. They are hard. They are expensive. They require technologies we do not yet possess. But they are problems of the external world, problems of physics, materials, and energy. The hardest problem of the Andromeda mission may be internal. It may be human. Consider what the crew of this ship is actually being asked to endure. They board the vessel knowing they will never return. Not that return will be difficult or expensive or take a long time. They know they will never return. Full stop. The world they are leaving will not exist in any recognizable form by the time they arrive at their destination. Every bond they have to the civilization, culture, and community that made them who they are is being severed permanently at the moment of departure. Then they spend somewhere between 20 and 50 years in an enclosed metal container, moving through space at near light speed. No sunlight, no seasons, no wind, no rain, no horizon, no open sky, no privacy in any absolute sense. The ship's walls are always close, the same faces always present. No news from home, because home is moving forward through time at a rate incomprehensible to contemplate. Any message sent to Earth would take 2.5 million years to arrive. Any response would take another 2.5 million years to return. Communication with the civilization that launched the mission is, for all practical purposes, impossible from the moment of departure. The crew is alone. Not in the Antarctic expedition sense, where isolation is temporary, resupply is coming, and the satellite phone still works. Not in the submarine sense, where the tour of duty has a fixed end date and home is waiting. Alone, in a way that no human being has ever experienced. Separated from the rest of humanity, not just by space, but by time, by the irreversible forward motion of a universe that will have moved on without them. Research on isolated groups, polar stations, nuclear submarines, the International Space Station, psychological experiments in isolation chambers reveals consistent patterns that play out over time with almost predictable regularity. The first phase is excitement, a new mission, new colleagues, new purpose. Energy is high and conflicts are few. People are focused on tasks, motivated by novelty, held together by shared purpose. This phase is exhilarating and real, but it does not last. The second phase is adaptation. Routines form, roles settle. The group establishes its rhythms, and with routine comes the gradual emergence of friction. Small habits become irritants. Someone's sense of humor that seemed charming at first becomes grating at month 6. Personality differences that were interesting at the start of the mission become fault lines along which tensions accumulate. The same conversations happen too many times. In normal isolation scenarios, Antarctic bases, submarines, space stations, people endure this phase because it is temporary. They know when it ends. The knowledge that departure is coming is itself a resource, a reserve of patience that can be drawn upon. Even the most difficult colleague is tolerable when you know you will see them for only another 90 days. On the Andromeda ship, there is no such reserve. The person who irritates you today will be beside you tomorrow, and next year, and in 20 years. You cannot request a transfer. You cannot take a vacation from them. You cannot even take a long walk to clear your head, because the ship's corridors are a fixed and finite space. The crew must be selected with extraordinary care, not just for technical competence, but for specific psychological qualities that do not always correlate with technical ability. Emotional stability, conflict tolerance, the ability to maintain warmth and genuine connection with others under prolonged stress. Self-awareness, the capacity to manage one's own internal states without external help. And the ship must be designed around these psychological realities. Private spaces, actual, acoustically isolated private spaces where individuals can retreat from the collective. Not merely separate bunks, but real rooms with doors that close. Common areas, large enough that people can spend time together without being on top of one another. Rotation systems that vary who works with whom and what tasks each person performs, preventing the kind of stagnant role calcification that breeds resentment. The ship would likely need trained mediators, crew members with backgrounds in psychology or conflict resolution, whose role is explicitly to manage interpersonal dynamics rather than technical systems. It might carry an AI system specifically designed for therapeutic support, available to any crew member who needs to talk without involving another human being. But here is the truth that no amount of design or preparation can fully address. In any serious isolation scenario, the possibility of catastrophic individual failure is real. People develop mental illness. People break down in ways that no psychological screening could have predicted. People become violent. People become suicidal. People become so profoundly impaired that they can no longer fulfill their role, and their role on a spacecraft with a crew of dozens or hundreds is not optional. On Earth, we have responses to these situations: hospitalization, law enforcement, separation from the group, intensive treatment. On the Andromeda ship, none of these options exist in any meaningful form. You cannot hospitalize someone in a closed system. You cannot separate them from the group in any permanent way because the ship has no adequate space for isolation. You cannot send them home. The only options are medical sedation, cryogenic suspension, which carries its own serious risks, or, in the most extreme case, a decision no crew should ever have to face. And everyone aboard the ship knows this. They live with the knowledge that failure is not merely a personal setback, but a potential mission-ending catastrophe. The psychological weight of that knowledge, pressing down on every interaction and every decision, year after year, is difficult to overstate. This is, in many ways, the most genuinely terrifying aspect of the mission. Not radiation or mechanical failure or the void outside, but the interior landscape of a group of human beings isolated beyond any previous human experience, trying to remain functional and cooperative and kind across the decades of a journey from which there is no return. The ship itself, architecture of a world. The ship that could carry humans to Andromeda would need to be unlike any vessel ever built. It would need to function simultaneously as a spacecraft, a radiation shield, a power plant, a hospital, a farm, a factory, a habitat, a research station, and a self-contained civilization. Every system would need redundancy. Every contingency would need a protocol. Every failure mode that could be anticipated would need a response plan, because there is no help coming and no possibility of resupply. Start with size. Research on long-duration isolated environments consistently suggests that the minimum personal space required to maintain psychological function is somewhere between 50 and 100 cubic meters per person, roughly the footprint of a small studio apartment. For a crew of 100, that is 5,000 to 10,000 cubic meters of living space alone. Add research laboratories, a medical facility adequate to handle everything from routine illness to major surgery. Workshops for fabrication and repair, storage for spare components, agricultural growing areas, and the mechanical spaces for life support, propulsion, and power systems. The total volume of the ship might be hundreds of thousands of cubic meters. The structure would likely be cylindrical and rotating. Rotation creates centrifugal acceleration, the tendency of everything inside to move outward along the radius, which functions exactly like gravity when experienced inside the rotating cylinder. The outer wall of the cylinder becomes the floor. Walk on it and you feel pushed outward, which feels like being pulled down. For a cylinder with a radius of about 100 meters rotating at roughly 2 revolutions per minute, the centrifugal acceleration at the outer wall equals Earth's gravitational pull. This matters profoundly for health. The human body evolved in a gravitational field. Without sustained gravity, bones lose density, muscles atrophy, cardiovascular function deteriorates. The vestibular system, the inner ear mechanisms that tell you which way is up, becomes confused and unreliable. For a journey measured in decades, even modest gravity is necessary for the crew to remain healthy and functional upon arrival. The cylinder must also serve as a radiation shield. Its walls must be thick enough and made of the right materials to attenuate the constant radiation environment of deep space. Water is an excellent radiation shield and could be used structurally in the walls, serving double duty as both shielding mass and water reserve. Polyethylene is lighter than many metals and provides good protection against cosmic rays. The specific design would require careful optimization between shielding effectiveness and structural mass. Power for the ship would come from nuclear reactors. Solar panels are useful only near stars, and once the ship has left the solar system and accelerated to near light speed, any particular star will be too distant for meaningful power collection. Nuclear fission reactors, the same basic technology that powers naval submarines and provides electricity in many countries, can run for decades on a relatively small fuel load and provide reliable, consistent power. The reactors would need to produce perhaps 10 to 20 megawatts of continuous power. This covers life support, lighting, agricultural systems, computing, navigation, medical equipment, manufacturing systems, and the various other power demands of a complex inhabited vessel. 10 to 20 megawatts is roughly comparable to the output of a small nuclear submarine reactor. Proven, achievable technology, though scaling it for decades of uninterrupted operation in deep space adds new engineering challenges. Redundancy is the governing principle for every system on the ship. 2 reactors, either of which can power critical systems alone if the other fails. 3 independent oxygen generation systems, any 2 of which can supply the crew if the third is offline. Multiple water recycling loops that can be isolated and repaired individually. Independent backup computers for navigation, life support monitoring, and communications. Spare components for every critical part, organized, catalogued, and accessible. Even with perfect redundancy, the ship will face failures over decades that could not have been anticipated. Components that no engineering team could have foreseen failing will fail. New failure modes will emerge from the interactions of complex systems operating in unprecedented conditions. The crew will need to improvise, to diagnose novel problems with limited information, devise solutions with limited materials, and implement repairs with limited expertise. This is why the crew cannot be composed only of specialists. Everyone must understand the ship's critical systems well enough to perform basic maintenance and emergency repairs. A ship's doctor who cannot diagnose a reactor anomaly is a liability. A propulsion engineer who cannot manage a hydroponics crop failure is a liability. The crew needs genuine versatility, deep expertise in their primary roles, combined with functional competence in every system aboard, feeding a crew across the void. Let us talk about something that sounds mundane compared to propulsion physics and radiation shielding, but is in practice one of the most complex challenges of the mission. Food. An adult human requires approximately 2,000 to 2,500 calories per day. This comes out to roughly 1 kilogram of food per person per day, depending on caloric density. For a crew of 100 people over a 30-year journey, you need on the order of 1 million kilograms of food. 1,000 metric tons. No ship could carry that mass, and no food could be stored for 30 years in edible condition. The only solution is to grow food aboard the ship continuously throughout the journey. Hydroponics, growing plants in nutrient-rich water rather than soil, is the obvious primary approach. It requires no soil, which saves significant mass. Water can be recycled. Plant waste can be broken down into nutrients and fed back into the system. Under artificial lighting designed to match the light spectrum plants actually use for photosynthesis, crops grow indoors with no weather variability and no seasonal constraint. But a hydroponic farm capable of feeding 100 people continuously for 30 years is a substantial installation. The caloric requirements alone demand significant growing area. Wheat and rice, the most calorie-dense crops practicable in a hydroponic context, require careful lighting and temperature management and produce food only at specific intervals after planting. The farm must be staggered, different sections at different stages of growth, so that harvest is occurring continuously rather than all at once. A failure in one section should not produce a food crisis for the entire crew. Beyond calories, the crew needs protein, fat, vitamins, and minerals in specific proportions. A monoculture of wheat will not sustain human health across decades. The farm must grow diverse crops. Leafy greens for vitamins, legumes for protein and complex carbohydrates, root vegetables for caloric density, fruiting plants for variety and micronutrients. Protein is a particular challenge. Complete proteins, containing all essential amino acids in the right proportions, are easier to obtain from animal sources than plant sources. Two solutions present themselves. The first is insect cultivation. Crickets, mealworms, and other insects can be raised in small, enclosed environments, fed on plant matter, and harvested for food. They are extraordinarily efficient converters of plant calories into animal protein, far more efficient than cattle or pigs or chickens. They require minimal space, they reproduce quickly, and the protein they provide is nutritionally complete. Many cultures around the world consume insects as a routine part of their diet. For a long-duration space mission, they represent a practical and sustainable protein source. The second is cultured meat. Growing animal cells in bioreactors without raising actual animals. A small sample of muscle cells from a chicken or a cow can be multiplied in a nutrient medium, fed with amino acids and growth factors, and harvested as actual meat tissue. No slaughter, no animal welfare concerns, no need for the enormous resources required to raise livestock. The technology is currently in early commercial development on Earth and advancing rapidly. Both approaches introduce new failure modes. Insect colonies can be wiped out by disease. Bioreactors can be contaminated. Any single-point failure in the protein supply must have a backup. Water is perhaps the most critical resource of all. Humans need approximately 2 to 3 liters of drinking water per day. Cooking, hygiene, and sanitation multiply this considerably. Agricultural systems require water. Cooling systems in the ship's reactors and computers may use water as a thermal medium. Total water consumption per person, accounting for all uses, might reach hundreds of liters per day. For 100 people over 30 years, this is hundreds of millions of liters, a quantity that cannot be carried. Every drop must be recycled. The International Space Station currently recovers approximately 93% of water used aboard, capturing humidity from the air, filtering and purifying wastewater, and returning it to the potable supply. The remaining 7% is lost, absorbed into materials, chemically altered, or not efficiently captured. 7% sounds small. Over 30 years, it is enormous. The Andromeda ship would need water recovery efficiency of 99% or higher. This means that the water you drink today was someone's perspiration last week, their urine 2 weeks ago, the condensation from their breath a month ago. This is psychologically challenging for many people and physiologically irrelevant. Water purified to the required standard is water, regardless of its previous form. The crew would need to understand and accept this reality before departure. Air recycling follows similar principles. Humans consume oxygen and exhale carbon dioxide. Plants and algae do the reverse. A balanced, closed ecosystem, plants consuming the crew's carbon dioxide and producing the oxygen the crew breathes. The crew's organic waste being broken down into nutrients for the plants is theoretically self-sustaining. In practice, the balance is never perfect. Oxygen production from plants varies with growth stage, light availability, and plant health. Carbon dioxide levels fluctuate with crew activity. Chemical scrubbers and buffer reserves of stored oxygen are essential to manage these fluctuations and provide emergency backup if the biological systems fail. If the agricultural systems catastrophically fail, a disease wiping out the crops, a power failure killing the algae tanks, a contamination event destroying the biological oxygen supply, the crew falls back on chemical systems and stored reserves. These are finite. Once exhausted, the oxygen is gone. The crew has hours to days. No single threat aboard the Andromeda ship is more immediately lethal than a failure of oxygen production. This is why the life support systems receive more redundancy than any other category of system aboard the ship. Not 2 backups, but 3. Not 3, but 4. Every component inspected continuously, every anomaly investigated immediately, every warning signal treated as urgent. Because the margin is absolute. The oxygen runs out, and everyone dies. There is no more fundamental constraint than that. Cryogenics, reproduction, and the problem of generations. We have been assuming in most of our discussion that the crew experiences the journey as a subjective period of 20 to 40 years, compressed by time dilation. But what if the ship cannot reach the velocities required for significant time dilation? What if the actual subjective experience of the journey is longer? At lower fractions of light speed, the crew could age substantially during the crossing. At 10% of light speed, the subjective journey time is essentially the same as the objective time. 25 million years. Obviously impossible. But even at 95% of light speed, the subjective journey takes roughly 800,000 years. No individual crew member could survive this. No family line could survive this without evolving into something unrecognizable. The mathematics simply do not work for a standard crewed mission at anything below roughly 99% of light speed. 2 approaches to this problem exist. The first is cryogenic suspension. Put the crew into a frozen state for the duration of the journey, slowing their metabolism so completely that biological aging essentially stops. Wake them upon arrival. They have not aged during the crossing. The ship flies itself, maintained by automated systems and perhaps a small rotating crew, while the rest of the complement sleeps. The appeal is obvious. The practical challenges are severe. Freezing biological tissue without destroying it is extraordinarily difficult. The fundamental problem is ice. When water freezes, it forms crystals with sharp edges that puncture cell membranes, rupturing delicate biological structures. The ice crystals that form inside a frozen human body cause damage at the cellular level that is difficult or impossible to repair upon thawing. Current approaches to cryogenics for preservation purposes use chemicals called cryoprotectants, substances that replace water inside cells with a compound that does not form damaging crystals, instead forming a glass-like amorphous solid at low temperatures. The body is perfused with these chemicals under precise conditions, cooled rapidly to prevent crystallization, and maintained at very low temperatures. Upon thawing, the cryoprotectants are flushed out and normal metabolism is restored. This works reasonably well for simple tissues, small organs, and some cell types. It does not yet reliably work for whole human beings, and in particular, it does not reliably work for the most complex and fragile structure in the body, the brain. Whole brain cryopreservation without neurological damage remains, at this point, genuinely unsolved. By the time humanity is building Andromeda ships, perhaps this will have changed. Perhaps the problem will be solved. Perhaps the technology will have advanced to the point where cryogenic suspension is reliable and routine. Perhaps not. If cryogenics is not available or not reliable, the crew is awake for the entire journey, subjective decades at relativistic speeds, or potentially much longer at lower velocities. The second approach for longer journeys is the generation ship. A generation ship is not built to carry a crew from departure to arrival. It is built to carry a society, a self-sustaining community of people who will reproduce during the journey, whose children will reproduce, and whose descendants, many generations hence, will be the ones who actually arrive. The original crew does not expect to complete the journey. They expect to live and die aboard the ship and leave its completion to those who come after. This sounds grim from certain perspectives. Children born into a generation ship do not choose their situation. They are born into an enclosed, predetermined environment with no option to leave, no external reference point for what normal life might be, and a mission assigned to them by ancestors they may never have met. They grow up knowing that the stars outside the windows are not their destination, that their destination is an abstraction, a described place their predecessors were moving toward when they were born. Maintaining purpose across generations is one of the deepest challenges a generation ship would face. The mission that motivated the founders may feel remote and abstract to the third generation, and meaningless or burdensome to the 10th. Cultural transmission, preserving not just the knowledge required to operate the ship, but the values, the motivation, and the emotional commitment that make the mission feel worth doing, requires deliberate, careful design. Stories, ceremonies, educational systems, social structures that keep the mission alive as a shared identity, rather than an inherited obligation. This is not unprecedented. Many human communities throughout history have maintained coherent identities across many generations in conditions of isolation or adversity. Religious communities in diaspora, indigenous cultures under colonial pressure, frontier societies separated from their places of origin by distance and time. The human capacity for cultural continuity across generations is real and documented. But doing it in a metal cylinder, moving through deep space with no external culture to draw upon and no possibility of contact with the broader human world, requires deliberate and sophisticated social engineering. The communities that managed to maintain coherent identities across generations on Earth had the world around them as a resource. The seasons, the landscape, the broader human social environment. The Andromeda ship has only itself, what the universe looks like at near light speed. Let us take a moment to inhabit the experience of the journey more directly. You are 4 years into the mission. The ship has completed its acceleration phase and is now cruising at 99.9999% of the speed of light. The engines have gone quiet, the vibration has stopped. The ship is no longer accelerating. It is simply moving, and will continue moving at this velocity until deceleration begins years or decades from now. You go to the observation area. There are no traditional windows. At near light speed, windows facing forward would emit radiation dangerous to the naked eye. But there are screens displaying what the ship's instruments detect, processed and adjusted to something human eyes can interpret. What you see is unlike any astronomical image ever captured from Earth. Directly ahead, where Andromeda lies, the view is compressed into a brilliant, concentrated disk. Light from hundreds of thousands of star systems, normally spread across a large arc of sky, has been Doppler shifted and aberrated into a narrow cone directly in front of you. The light is blue shifted. Stars that would normally appear yellowish or reddish glow blue-white. The entire disk is brighter than it should be, because you are running toward the photons rather than waiting for them to reach you, increasing the rate at which they arrive. At the very center of the disk, you can barely make out the suggestion of structure. The bright nucleus of Andromeda, the faint hint of spiral arms. But it is compressed and distorted, the whole galaxy squeezed by aberration into a fraction of its normal angular size. Turn around and look behind you. The screen is nearly black. The Milky Way, your home galaxy, the galaxy that contains every star humanity has ever seen from Earth, is behind you. Its light is redshifted, stretched to infrared and beyond. Certain instruments could detect it, but to visible light sensors, it has largely vanished. The galaxy that contained every human being who ever lived is receding into invisibility behind you. In a few more years of ship time, it will be undetectable. To the sides, the screen shows faint rings and arcs of light. The relativistic aberration has pushed stars from their normal positions in the sky toward the forward direction. Stars that would normally appear 90 degrees to your side now appear ahead of you. Stars that were almost directly behind you have migrated forward. The entire visible sky is being vacuumed toward the nose of the ship. The cosmic microwave background, normally invisible to human eyes, a uniform, faint radio glow, has been blue-shifted into visible wavelengths. The forward view glows with it slightly, a diffuse, added luminosity over everything ahead. You're experiencing the universe at a speed nothing alive has ever moved before. The physics you learned is working exactly as predicted, but that does not make the experience less alien. The sky you see is a sky that has never been seen from any vantage point in the history of life on Earth. It belongs entirely to you and your crew. Outside the ship, time is moving differently. On Earth, wherever Earth is now, 2.5 million light-years away and millions of years in the past, civilizations are rising and falling. Empires are building and crumbling. Millions of generations are being born and dying. Ice ages are coming and going. The sun is continuing its slow, imperceptible brightening. You experience none of this. From inside your ship, moving at near light speed, a day passes as a day. You sleep and wake. You eat and work and talk with your crewmates. The clocks aboard the ship run at their normal rate relative to you. Nothing feels wrong. Nothing feels dilated. Time, from the inside, is simply time, but outside, it is pouring forward at a rate that would be incomprehensible to watch. Your crewmates become something unusual, the only people in the universe moving at the same speed as you, experiencing the same dilated time, sharing the same impossibly rare perspective. You are all together on the same island in the flow of time, separated from the rest of reality by velocity, isolated not just in space, but in the architecture of space-time itself. This creates a form of intimacy unlike anything in ordinary human experience. Your crewmates are, literally, the only other beings in the universe experiencing the same time as you. Everyone else, every human on Earth, every hypothetical alien on any planet in the Milky Way, is on a different timeline. They are aging at a different rate. They are, in a precise physical sense, living in a different time than you. It is the most profound loneliness and the most profound companionship simultaneously. Arriving, deceleration, navigation, and what awaits. The deceleration begins. After decades of cruising, the exact duration depending on the ship's velocity and the crew's experience of time, the ship fires its engines against its direction of travel. The geometry inverts. What was the rear of the ship is now pointing forward as the engines provide thrust against the direction of motion, gradually reducing the ship's tremendous velocity. The physics of deceleration mirrors the physics of acceleration exactly, except in reverse. The energy cost is the same. The time required is the same. The technical challenges are the same. If you used 1/2 of your propellant reserves to accelerate, you need the other half to decelerate. Getting the balance right, having exactly enough propellant remaining to bring the ship to a manageable velocity, required precise planning decades ago at the moment of departure. As the ship slows, the aberrated universe begins to normalize. The concentrated disk of Andromeda ahead starts to spread outward. Stars that were compressed into the forward cone begin to migrate back toward their correct positions in the sky. The cosmic microwave background fades back toward invisibility. The universe reassembles itself into something resembling normalcy as the ship's velocity decreases. And Andromeda grows. What was a disk of compressed light becomes a disk of genuine structure. Individual features become visible. The bright galactic nucleus, a dense region of stars, and, at its very center, a supermassive black hole, 4 times more massive than our own Milky Way's central black hole, glows intensely. Dust lanes thread through the galactic plane. Regions of active star formation blaze with the light of newborn massive stars, brilliant and blue-white. The spiral arms resolve, sweeping outward from the nucleus. This is a galaxy. An entire galaxy approaching. 1 trillion stars. The crew has been analyzing Andromeda throughout the journey, using the ship's telescopes to study the galaxy in increasing detail as the distance closes. They have identified candidate star systems, yellow dwarf stars similar to our Sun, at distances from their host stars that put any orbiting planets in the habitable zone where liquid water could exist. They have used spectroscopy to look for atmospheric signatures, the presence of water vapor, oxygen, carbon dioxide, methane, that might indicate conditions suitable for life or for human habitation. Now they must choose their destination within the galaxy and navigate toward it. This is not trivial. The galaxy is 220,000 light-years across. Andromeda, from the crew's current perspective as they decelerate toward it, is an entire universe of its own, vast beyond easy comprehension, containing regions of diverse density, different stellar populations, regions of heavy star formation, and regions of relative quiet. Picking a target and navigating to it while still decelerating from near light speed requires careful calculation and precise maneuvering. The ship enters the outer regions of the galaxy. For the first time in decades, individual stars are visible as distinct points of light rather than a compressed blur. Stars that belong to Andromeda, not to the Milky Way. The crew is inside a different galaxy. That fact is real, verifiable, and extraordinary. Ahead lies the target star system, a yellow dwarf star, planets in orbit. The instruments indicate a world in the habitable zone, the right distance for liquid water to exist on the surface. Spectroscopic analysis, imprecise at this range but suggestive, indicates an atmosphere with water vapor and perhaps oxygen, perhaps life, perhaps conditions that could support a human colony, perhaps both. The ship decelerates further. Weeks of deceleration bring it from interstellar velocities to something manageable on a stellar scale. It enters the gravitational domain of the target star. Planets become visible through the telescopes as distinct shapes rather than points of light. And there it is, a world, blue-green and shrouded in clouds, orbiting a star that looks reassuringly similar to the Sun. A planet with an atmosphere. A planet, possibly, with oceans. After a journey measured in decades of subjective time, crossing 2.537 million light-years through the intergalactic void, the ship goes into orbit around an alien world in another galaxy. The crew gathers at the observation screens. There are no adequate words for this moment. Somewhere behind them, 2.537 million light-years away, and millions of years in the past as they experience time now, Earth exists, or existed. The Milky Way shines as a faint smudge in Andromeda's sky, a galaxy-sized reminder of where this mission began. A new world. What they find, what they built. Now comes the question that all the physics and engineering have been building toward. What do they find? If the world below is habitable, if its atmosphere can be breathed, its surface walked upon, its water drunk without lethal consequences, then the mission has achieved the best possible outcome. The crew establishes a surface presence, a first landing, samples collected, analyzed, catalogued. The ship's sensors sweep the surface for pathogens, chemical hazards, atmospheric inconsistencies that could be lethal. If the planet is safe, the work of building begins. Prefabricated habitat modules deployed from the ship, power systems using the ship's reactors, water extracted and purified from local sources, rivers, lakes, ice deposits. Food production expanded using local soil or hydroponic systems transplanted from the ship. The ship itself, which served as home for decades, becomes a resource. Its components scavenged, repurposed, integrated into the growing infrastructure of the colony. Children are born, the first human beings born in another galaxy. They grow up under an alien sky, with unfamiliar stars and the Milky Way visible as a faint smudge on clear nights. To them, Earth is not a memory or a longing. It is a history, a place their parents and grandparents described that exists in recordings and stories, but not in any living experience. They are, in a meaningful sense, a new kind of human, born in Andromeda, shaped by this world's gravity, this sun's light, this planet's resources. Their biology is the same as their ancestors, but their context is entirely different. They are Andromedans. Over generations, the colony grows. More area is cultivated, more infrastructure is built. The population increases. The skills and knowledge brought from Earth, preserved in the ship's databases, and passed down through education, form the foundation of a new civilization. Eventually, these people may build their own ships. They may explore the surrounding region of Andromeda, visit neighboring star systems, establish new outposts. The process repeats on a smaller scale. The exploration expands. A new branch of humanity, rooted in a different galaxy, begins its own exploration of the universe. But this is the optimistic scenario. If the planet below is not habitable, if the atmosphere is toxic, the surface too cold or too hot, the chemistry incompatible with human biology, the situation is more difficult. The crew must live in the ship, or in sealed habitat modules assembled on the surface or in orbit. They mine local resources, water ice, metals, silicates, to extend their supplies. They build and maintain a controlled bubble of Earth-like conditions in an alien environment. They survive, but not freely. And there is a third possibility, the one that no amount of pre-departure planning could fully prepare for. What if something is already there? Contact, isolation, and the Fermi question. The Andromeda Galaxy contains approximately 1 trillion stars. Statistically, a significant fraction of those stars host planetary systems. A fraction of those systems contain planets in habitable zones. A fraction of those habitable planets have developed life. And a fraction of those living worlds have produced intelligence. Or perhaps none of them have. The statistics are completely unknown. This is the Fermi paradox applied at galactic scale. If intelligent life is common, we might expect the universe to be full of evidence of it. Radio signals, megastructures, artifacts visible across astronomical distances. We have detected nothing of the sort. Either intelligent life is extraordinarily rare, or it tends to destroy itself before becoming capable of producing detectable signatures. Or the universe is so vast that even a civilization broadcasting actively for millions of years has not yet had its signal reach us. Or intelligent life exists in forms we have not learned to detect. The crew of the Andromeda ship would arrive with this uncertainty unresolved. They would be the first to be in a position to answer the question with any direct evidence. If they find a barren world, no life at all, not even microbial, that is itself a profound data point. It suggests that life may be genuinely rare. It makes the journey both lonelier and more precious. If they find microbial life, the kind of simple, single-celled organisms that dominated Earth for the first 3 billion years of its biological history, that is an extraordinary discovery. It means life arose independently in 2 galaxies. It makes life seem common, perhaps universal. It raises immediate questions about contamination, whether human presence on the planet might harm the existing biology, or whether the existing biology might be hazardous to humans. If they find complex life, multicellular organisms, ecosystems, anything resembling the diversity of Earth's biosphere, the ethical questions become severe. Do humans have the right to colonize a world that is already biologically inhabited? What obligations do they have to the existing ecosystem? These questions were debated on Earth in the context of land exploration and colonial history. In Andromeda, there is no external authority to appeal to. The crew makes their own decisions and lives with the consequences. And if they find intelligence, if they arrive in a star system in Andromeda and detect artifacts, structures, signals, or beings that demonstrate organized intelligence, this would be the most significant discovery in the history of human awareness. The moment of first contact with an extraterrestrial intelligence, occurring not in our own galaxy, but in another one, 2.5 million light-years from home. How would it go? No one can know. The history of contact between human cultures on Earth, which at least shared basic biology, planetary environment, and cognitive architecture, provides a cautionary template. Contact between cultures at different technological levels has, throughout human history, often gone badly for the less powerful party. Sometimes it has gone surprisingly well. Context, temperament, specific circumstances, and chance all played roles. Alien intelligence, if it exists, might have a cognitive architecture so different from ours that communication is not merely difficult, but genuinely impossible. Our concepts of language, mathematics, and logical structure are deeply embedded in human evolutionary history. Whether these concepts would translate to a mind that evolved under entirely different conditions is unknown. We assume mathematics is universal because mathematical truth does not depend on biology. But whether a being evolved under radically different conditions would recognize our mathematics as the same thing they practice is genuinely uncertain. The crew would have protocols, guidelines for how to approach a potential contact situation, procedures for signaling peaceful intent, caution against actions that might be misread as threats. These protocols would be developed by experts in linguistics, anthropology, psychology, and evolutionary biology. But they would be built on a foundation of complete ignorance about the specific intelligence being contacted. They would be best guesses. First contact, if it happened, would be improvised, adapted in real time. The crew would be making one of the most consequential series of decisions in human history, with no precedent to draw upon and no authority to consult. And there is the hostile scenario. The possibility that whatever intelligence exists in Andromeda does not regard the arrival of a human ship as a neutral event. that our arrival is seen as intrusion, as threat, as competition for resources, or simply as an opportunity. The crew would be 2.5 million light-years from any help. They would have the technology they brought with them, and nothing more. If the encounter turned hostile, and the opposing intelligence was significantly more advanced, which, given the possibility of civilizations millions of years older than ours, is a real possibility, the crew would have essentially no options. Retreat to where? They came 2.5 million light-years. They have consumed most of their propellant. There is no flight path back to Earth that is achievable with remaining resources. This is the existential vulnerability of the mission. Every planning assumption made on Earth is based on observations made from 2.5 million light-years away, seeing the galaxy as it was 2.5 million years ago. What actually exists in Andromeda at the moment of arrival, the civilizations, the physics, the threats, is entirely unknown. The crew commits to a destination they cannot verify until they arrive, with no ability to change course once they are there. Energy, ethics, and why we go anyway. We have covered extraordinary ground. The physics of relativistic travel, the engineering of a ship that must survive for decades in deep space, the biology of keeping humans alive without resupply, the psychology of long-duration isolation, the uncertainty of what awaits at the destination. Let us now step back and ask the largest question. Why? Why would any civilization undertake something so difficult, so dangerous, so uncertain, at such colossal cost? The energy requirements alone are staggering. To accelerate a 10,000-ton spacecraft to 99% of the speed of light requires approximately 900,000 times the total energy humanity currently produces in an entire year. The energy output of the Sun for several hours concentrated into the propulsion system of a single vessel. Building the infrastructure to generate and direct this energy, laser arrays, particle accelerators, power stations of unprecedented scale, would require the economic output of an advanced civilization sustained over generations. The materials required would challenge any known manufacturing capacity. The engineering problems to be solved would require scientific breakthroughs we cannot currently predict. The time from conception to launch would likely span centuries. And at the end of all of this, the crew might perish in transit, or arrive to find an uninhabitable destination, or encounter something that ends the mission. There is no guarantee of success. So the question is not merely whether we could attempt the journey. The question is whether we should. One argument is survival. Earth is not permanent. The Sun will expand into a red giant in roughly 5 billion years, making the inner solar system uninhabitable long before it physically swallows Earth. On much shorter timescales, a large asteroid impact, a nearby gamma-ray burst, a runaway greenhouse effect, or a dozen other catastrophes could threaten civilization or the species. Spreading humanity beyond Earth, beyond the solar system, beyond the galaxy, is an insurance policy against extinction. But Andromeda is not the nearest insurance policy. The solar system has other planets and moons. Nearby star systems within a few dozen light-years offer more accessible alternatives. If survival is the motivation, colonizing within our own galaxy makes more immediate practical sense. Another argument is curiosity. Humans explore because we explore. It is built into our behavioral repertoire as a species, the tendency to move toward the unknown, to investigate the unfamiliar, to seek the horizon. The Polynesians crossed the Pacific in outrigger canoes, guided by stars and wave patterns, finding island after island in open ocean. Ferdinand Magellan's expedition circumnavigated the Earth with 16th century technology. 5 ships departed, 1 returned. 18 survivors from 270 who began the journey, and in doing so, proved that the world could be circumnavigated. Robert Falcon Scott died on the return from the South Pole, having arrived to find Roald Amundsen had beaten him there. But the scientific data his expedition collected contributed lasting value to human knowledge. Exploration has always been expensive. It has always been dangerous. People have always died doing it. And it has always produced knowledge, technology, and understanding that could not have been obtained any other way. The journey to Andromeda is exploration taken to its absolute maximum. The farthest destination reachable within what we currently understand to be possible physics. The ultimate expression of the impulse that has driven our species to every continent, every ocean, every world in our solar system. There is also an argument from ethics, specifically from the ethics of investment. The resources required for an Andromeda mission are not nothing. They are colossal. Energy that could power civilizations, materials that could build habitats for billions, scientific talent that could address countless other challenges. Is it ethical to commit these resources to a mission that benefits a crew of hundreds, while billions of people face poverty, disease, and environmental degradation? This tension is real and has no easy resolution. Throughout history, societies have debated the allocation of resources between exploration and domestic improvement. The Apollo program, the most expensive scientific and engineering project in human history to that point, consumed resources that might have been deployed differently, and it also produced advances in computing, material science, and telecommunications that have benefited hundreds of millions of people. The technologies required for a mission of the most extreme difficulty often find applications that their designers never anticipated. But perhaps the most honest answer to why is simply this. Because the alternative is accepting that there are places we can see and can never reach, distances we can measure and can never cross, that the universe contains wonders that exist permanently beyond our grasp, not because they are impossible in principle, but because we chose not to try. That is a choice. It is a legitimate choice, and there are good arguments for it. But it is also a choice that many people, looking up at that faint smudge in the night sky, find they cannot make. When you see Andromeda in the sky tonight, and you can see it on any clear, dark night, a soft, pale blur in the constellation it shares its name with, you are looking at 1 trillion stars. You are seeing light that left that galaxy before our species existed. You are witnessing a destination that is simultaneously visible and beyond reach, known and unknowable, close enough to see and far enough that even light takes 2.5 million years to cross the distance. It is the furthest thing our unaided eyes can see. And it is there every night, waiting. The universe is not asking us to reach it. The universe does not care. But we look up and we see it, and something in us asks the question anyway. Can we? We have covered 2.537 million light years tonight without leaving where you are. We have walked through the physics of a universe that makes the journey almost, but not quite, impossible. We have designed ships that do not yet exist, fueled by energy sources we have not yet mastered, crewed by human beings who would need to be extraordinary in ways we have never fully tested. We have thought about radiation and dust and deceleration and food and oxygen and water and the long, quiet weight of isolation. We have asked what waits at the destination and found that we do not know, and that the not knowing is itself one of the most honest and profound truths about where we stand as a species. Andromeda is still there. It was there before any human being existed. It will be there after we are gone. It does not need us to look at it or think about it or dream about reaching it. But we do look, and we do think, and we do dream. That is what makes us what we are. Right now, wherever you are, let your body settle fully. Let the weight of all of this, the physics and the distances and the questions, dissolve into the quiet. You do not need to hold any of it. It will all be there tomorrow. The calculations will not change. Andromeda will not move. Right now, there is only this moment. Your breath, slow and steady. The dark around you. The particular silence of wherever you are. Let your thoughts drift like distant light, present for a moment, then moving on, then gone. Somewhere in the night sky, a faint smudge of light holds 1 trillion stars. And it is enough, for now, simply to know it is there. Sleep.